right, everybody. Hope everybody had a great break. We've got a nice long session up next, covering some structural design and integration of OpenVSP structures with Brian Sandoz with Versatile Arrow. So these have historically been really interesting and very complex talks. So if you want to really see some heavy use case of OpenVSP and structures, this is going to be right up your alley. So, Brian, you're welcome to go ahead and roll into your talk, sir.
All right. Hello. So my name is Brian Sandoz. I'm a consultant that works in kind of aircraft design, conceptual design stuff. And I've been working with OpenVSP and trying to develop a lot of workflows specifically around mass fraction and structural mass fraction, and kind of incorporating like aero configuration to loads to structural analysis at a very conceptual level in order to sort of feed that early stages into a program, give some mass fractions that are, sort of physics based. So I'm going to have I have about 2 hours today. I have a demo in the middle where I'm going to kind of attempt to go from a base VSP model to a FEA result using only open source tools, and that'll take about an hour. At the beginning of that, I think I have about 45 minutes I'm going to talk through right now with you about sort of the structures workflow that I use, possible workflows, and then a bunch of tools and tips, mostly as sort of a reference for future use. When you're thinking about starting to do a structures work, you can pull this up, look at the slide deck, and kind of remind yourself, oh, that's right, this little feature does this little feature does that, because it is very detailed, and there are a lot of there's a lot of repetitive work in structures, and it's helpful to be able to make that efficient. And at the end, just for fun, I have a little bit of a show and tell, show you some kind of funky things that you can do with it, and also spin those models if people are interested and answer questions. So what I'm going to cover in this first talk is why should we do structural analysis at the conceptual level? It's sometimes a part of the program that's more detailed and very intensive and a lot of work and a lot of time. It tends to get pushed more into the detailed design phase or preliminary detailed design phases, critical design, things like that. I'm going to talk through a workflow tool chain that I use, as well as some sort of resources for you for tool chains, workflows, and things like material properties. I'm going to talk a little bit about external loads. Loads in and of itself as a topic is a very big topic, and there's certain ways we can go about generating loads in order to actually generate an analysis where we can size our structure. And then I'm going to go through sort of an extensive tips and tricks like I just mentioned. So the why question for conventional aircraft construction. So we often use a structural mass fraction, and we can pull that from a variety of resources, typically based on historical data. We have NDARC, which can be used for, as sort of mass methods. There's various aircraft design books all have different mass buildup methods, and those tend to work well if you're doing a helicopter or a transport aircraft, and sometimes even a general aviation aircraft. But for things like UAVs or novel configurations like we're seeing with a lot of the VTOL or eSTOL or eVTOL, or in my case, flying cars, roadable aircraft, those conventions tend to break down and they're not as accurate. Also, for scale, a lot of the large aircraft is where the data is. And so if you're doing a UAV, things start to kind of fall apart when you're estimating a mass fraction. And getting that mass fraction wrong can cause a lot of problems, because it can ultimately lead you to think you can do things that you can't. And that's part of the reason why I'm sort of working to develop this conceptual level structural analysis built into all the other tools that OpenVSP provides for conceptual analysis, both in the design and layout, configuration, and then also in the aero and the stability control and sizing aero structures, and then also being able to take that and now get a mass fraction and kind of iterate inside that loop to get what I would call sort of a physics-based mass fraction. So there's a couple, options here. The one that we're going to talk about today is parametric FEMs from OpenVSP. And why I put parametric FEM in parentheses because parametricity is usually requires some work no matter where you are, whether you're in CAD or in OpenVSP. You will always have to mess with and fix your FEM after you make changes to your VSP model. But the idea is if you lay out a bunch of ribs and spars and you make the wing bigger in aspect ratio, or you make the chord with the root bigger, then everything kind of falls along with that. And it's not that you can't do that in CAD, it's just it becomes a little more disconnected from the fundamental concept of the wing, having a root chord and a tip chord, or you have to generate all of that by hand through formulas and things like that. It's still a work in progress, but it's getting very useful. I personally am able to use it in my job to build FEMs and run them and get sizing out of it. It's more visual than hand calculations, which are sort of what I would call the other major option. But it does require understanding of FEA and understanding on a level of a structural analyst to be able to size the structure using FEA. If you're to use hand calculations, that takes a long time to set up, sometimes lug calculations and fitting calculations and box structure sizing calculations for a novel aircraft. There's more simplification in the geometry. A few more assumptions have to be made. Once you have created it, you can iterate on it fast. But if you're sort of, if you started a startup, then you have a pretty large amount of effort to create those hand tools by hand. There's also a blend. You can, a lot of those hand tools work really well for generating attachment points and things like that OpenVSP's structures tool does not really address. So there's also a combination of the two. And then, of course, there's also specialized structures like the M4, or specialized tools like the M4 Structure Studio that do this as well. So this is a slide that I've presented before. I've kind of shortened it a little bit, but this is sort of the cycle of a workflow to get to a viable design. So you start with some initial sizing, some sketches, you make a VSP model of that, you do some VSP aero surface sizing to get the tail the right size relative to the wing. This is sort of more of the aircraft configuration stuff. From that, you derive some basic performance and V-speed information. And then from that, you can kind of come up with some one-page or sort of very fundamentally basic load cases. You can do FEA structural analysis all day long, but if you don't have loads, you don't really have anything to start from. So then you do a structural layout in VSP. You can make what I'm calling sort of a lo-fi FEM, or what's often called a global FEM or a loads FEM. You can use that to size the structure and you can get to a viable design. Now, the reality is you end up bouncing back and forth between all of these different things, as you should at the conceptual level when you're iterating. The nice ability of this tool is you can go into the structure stuff, start laying out internal structure and realize, hey, wait, this doesn't make sense. I can't put a bulkhead here because it doesn't fit, or the structure, the OML isn't the right size. You can immediately go back up to the OML and change the wing or change the fuselage, run some of your VSP stuff, VSP aero stuff, make sure that still works for what your requirements are. Rederive maybe some changes to performance and V speeds and get some new load cases, and then go back to the structural layout. So that's kind of the general workflow. And when we talk about tools here, so there's 3 sections of that kind of require external tools to OpenVSP. So load case definition using Excel or Python or MATLAB or text. That's derived from some resources that I'll show later on. There's also pre and post processing. Now, pre-processing is what VSP is doing for us, right? It's building a structural mesh and in some cases boundary conditions and loads. But you also need to be able to post-process and look at the results and look at the strains and look at the beam forces and figure out where you are on your sizing, and then go back to the structures, change sizes, thicknesses of shells, and then go back and reanalyze. So for those post-processing tools, there's many tools that you can use for this. There's a series of open source ones like PyNastran GUI, which is what I'm going to demonstrate today. And then, of course, there's FEMAP and Patran and HyperWorks and ANSYS or Abacus, all these paid for, MechWay, paid for tools for pre and post processing. Then for analysis, we have solvers that we need to solve the structural analysis with. The kind of Rob sort of went through some of these, but the one that I'm going to be working with is MyStran. As also Calculix is kind of embedded in VSP and VSP Aero, and I'll use some aspects of calculus as well, but not the solver. So this is the tool chain kind of put together. What I'm going to kind of show after we go through these tips and tricks is a combination of OpenVSP, using Python and Excel to define some load cases, PyNastran GUI, which is really a post processor, but also sort of a partial preprocessor, and then MyStran as a solver. And MyStran is an open source solver which processes Nastran formatted input decks, which is really great because particularly with the aerospace industry, the Nastran is sort of more of the predominant format for analysis. So HyperWorks uses it, Siemens NX and all of the Siemens Nastran drive products use it, and all of MSC, of course, uses Nastran as well. So there are also other Abacus and ANSYS ways to do things, but aligning with sort of the industry approach is really helpful. And as Rob kind of showed you, both Nastran formatted output and Abacus/Calculus formatted outputs come out of the structures tool. One thing I will kind of put a shout out to the MyStran folks. So they're developing this out of pocket right now, which is really awesome. If folks have any way to help with that, the current work that they're doing is to improve the shell element formulation, including shell buckling, and also higher order, those mid-side nodes that Rob talked about. Their new shell element will have the ability to do mid-side nodes or second order shells. So that's really exciting. And with that, kind of adding those components, they now really have, they will very soon have what I call a fully functional solver for what we're doing here. Now, there's other things it doesn't quite do, but for the conceptual structural analysis that we're doing here, once you kind of get buckling in there to be able to size acreage and panels, skin panels for buckling, then you now kind of have a closed loop with open source tools, which is really great. One thing we'll recommend is compiling from the source to capture all of their current updates, since it really is a sort of work in progress right now. There's also an impending 16.0 release with these new shells, which will show a lot of improvement in the shell formulation, and of course also address things like buckling. So talking about loads. So loads are tricky. Loads take a long time. We don't have a lot of time in the conceptual phase, so we need to have some resources. So I've listed these here. We won't go through all of them in detail or anything like that, but this is mostly just a list for you to go start finding standards or finding Part 23 requirements for loads, so you can use that to learn how to generate your own one-page or conceptual loads. So an example of that for just symmetrical maneuvers, so pull-ups, pushovers, things like that, things that typically exercise the wing, we can create what's called a VN diagram. That's a speed and load factor diagram you see down there in the lower left, and these are available in lots of resources. They're also covered in a lot of textbooks for how to generate those, but you'll need to generate something like that for your vehicle, and we'll go over that a little bit in the demo. And then we need to pick a representative symmetrical maneuver case from that, basically one of these corners or a couple of these corners. So I typically pick like A or D for a positive limit load factor maneuvering, and then G or E for a negative limit load factor maneuvering case. So you have an up bending and you have a down bending. They tend to be somewhat similar between the slower speed ones, A and G, and the faster speed ones, D and E. Now, it's not always true, but if we're just trying to get a really rough hack at a weight from a physics-based approach, we don't necessarily need to do what you would normally do and what you will later do for structural analysis, which is run all of the corners and make sure that you've captured all of the critical load cases. So then we'll derive some VSP Aero flight conditions based on these load cases, and we'll run VSP Aero, and then we will run the VSP Aero structural coupling to grab those pressures out of VSP Aero and apply them to the aero surfaces. Then you do that again for a negative G maneuver, and then if you're trying to size like a wing, like we're going to work on, you can do that for an asymmetrical maneuver or a roll, something that gives you sort of a max torsion. So now you're exercising the wing up in bending, so you're compressing the upper skin, and then you're exercising the wing in a down bending, so you're compressing the lower skin, and then you're exercising the wing in torsion. So you've kind of captured the primary load paths that would cause you to size up various parts of the structure. This is just a shout out to tail loads, which there are simplified methods for tail loads to generate. They do not take a lot of time to create, but they take a lot of time to understand what they mean and how to apply them. So I just recommend looking at these ASTM specs, trying to wrap your head around it. And then if you're going to go do tail loads and you want to use simplified loads, kind of come back to this and review those. You can also do tail loads with VSP Aero. It becomes a little more tricky because you're having to kind of get balancing in there and trim the aircraft and then do a deflection, things like that. But that's certainly more the approach that is used more commonly these days. So this is just a list of where to get material properties. Kind of like with loads, you can't do anything without allowables. You don't know how strong to make the structure unless you have your material properties and your strength allowables, things like that. For metallic, this is often much easier. Mill Handbook 5, which is the public version of MMPDS, is kind of the gold standard for material properties and allowables. For composites, it gets a little more tricky. There is a public database that we often use called the Agate database or NCAMP database. That has also been put into a paid product called CMH17. And that gets you lamina properties, and then you have to build up laminate properties. Now, Rob has built in classical laminate theory so that you can put in just lamina properties, and it will derive laminate properties for the structures tool. So that's really great. It will output orthotropic laminate, sort of smeared or consolidated laminate properties. It does not output what we call a P-comp in Nastran terminology, which is a property card that actually has all of the lamina in it and their orientations. And that is something that Nastran or Maestran can use, and it will actually use that for failure theory analysis like Hoffman or Sci-Hill or Sci-Wu. And those are failure theory analysis sort of analogous to writing margins on metallic parts against like a von Mises stress or something. So I've tested FEMAP NX Nastran I've tested this with FEMAP and NX Nastran, Maestran, and then a little bit with Calculix. This is kind of a breakdown of the most relevant features. I think the key parts of this is Maestran doesn't really have buckling yet, but we're for shells, but that's being worked on. And Calculix doesn't really do shell analysis. It expands everything to a solid representation and runs a solid mesh and doesn't have a shell element formulation. So that can be a little tricky with the types of structures that we're talking about here, where shell elements are a true shell element representation is a much more efficient and often easier to kind of handle methodology. So of these, NX Navstrand obviously is what you pay for, and so you get all of the features. MyStrand is sort of working to become a good open source alternative, and Calculix is it's sort of pulling Calculix a little bit out of its happy place to use it for these kinds of structures. So a key tip and trick here, you will need some fundamental stress analysis training or skills, or have somebody who can help you with this. This isn't something that you can kind of just jump into without any FEA analysis experience, because the VSP will make a mesh, but it will not necessarily run. And depending on what solver you're using, you may get varying levels of feedback as to what broke and what didn't break. So that can be a little challenging if you're trying to troubleshoot mesh, but you don't really know how to read what's a Jacobian, non-positive Jacobian determinant, or what's a warped mesh, or what's an aspect ratio. So getting some training in that part will sort of help you be able to mesh better in VSP to get meshes out that will work. Okay, so now I'm going to start running through a bunch of these tips and tricks. One important one that I have had to kind of stop myself from doing several times is it's easy to get obsessed with symmetry and accuracy in VSP structures. I would highly recommend that you don't. Once you have created a design with a notional layout for an internal structures, you're going to hand this off to a structures team or to a structures consultancy, and they're going to do a real detailed or even a preliminary detailed structural analysis design with real loads and real material properties. That's not what you're trying to do here. Your goal here is to just get a better than convention weight estimate with some sort of a buffer. So you're trying to be able to tell the design team, hey, we need to actually make the fuselage 6 inches bigger in diameter, because the structural stuff, just the weight goes down by like a lot if you just increase that diameter. Can we do that? Can Aero do that? Long before, all of the lines have been frozen or the OML is locked or things like that, where now you can't mess with any of that. So my example here is, I put all these fixed points in this ring around this fuselage structure for attachment to the aft of the fuselage. And I spent a lot of time making sure that the left side and the right side were lined up and that it was all symmetric and all equally spaced. And did I really need to do that? Or should I just kind of have slapped a bunch of points around and then visually looked at the other piece and slapped a bunch of points around and connected things up? It's sloppy, yes, but again, we're trying to get a Waggett weight that's better than scaling down a 747 to a UAV. So that's sort of a soapbox there a little bit, or something that I feel is important when we're thinking about VSP structures. It's a little too easy to make it good, and we're trying to make it good. We're just trying to make it good enough. So one thing that will cause meshes to fail is if you try and line up structure internally. So on the left image here, I tried to line up this bulkhead and this sort of floor, and I did it visually and kind of got them, close, but the mesh kept failing because there was these infinitesimally small elements that it was trying to create there that were below my minimum element size, and it would bomb. So, again, with the making things perfect, you may be like, well, I don't really want the floor exactly there. It should be like a little bit higher, a little bit lower in reality. And yes, you will be able to do that later in reality. But for this process, just put it kind of relatively close. And you might have to do that to get away from meshing issues, because of the methodology here is about speed and getting a very complicated mesh built really quickly. That's sort of a rough or coarse approximation of your structure. So you can use rectangles often to delineate chord panels on wings, or in this case for this airplane, there was a ply layup that was done in sort of patches on the solid core wing. So I layered a bunch of rectangles, and when you're doing that, the upper one in the tree will dominate. So you can organize your layers so that they go from top to bottom, and then that will show up on your in your structure. If you were to grab the bottom, the biggest panel here, and move it to the top, it would just blow away the properties for anything inside of it, and you would just get a big blue rectangle there. So it would only be one property. It wouldn't capture the rest of the layout. So this is kind of an efficiency thing when you're creating a bunch of fixed points and you're connecting structure together. I find it's really easy to pick, or it's really important to pick like a left front, left rear, right rear organization, something that makes sense to you going around clockwise or counterclockwise, but just do it the same way on all the structure. And then that way, because this is sort of a tedious part of it, is hooking each of these up individually. I got to connect this one to this one, this one to this one. And if you have them all lined up in the same order on the two different components that you're trying to connect to, then the way VSP's dialog boxes work, it makes it really easy to just drop down to the next one and the next one. Everything kind of cycles up at the same order, and it's really easy to just kind of click through and connect structure together. One thing that I have started doing more recently is don't forget that you can, even though you're in the structures GUI, and when you open up the structures GUI, everything disappears on the VSP screen and only starts showing you the structures thing. That doesn't mean that you can't go add in wheels or tires or wings or backgrounds to help you with your structural things, other components. So in this case, on the left, I'm meshing the fuselage structure, but I've pulled in the wing and the tail so that I can kind of see where things line up, so I can put my fixed points where I want spars to be. You can't in the FEA structures GUI show two different structures at the same time. You have to use the assembly GUI for that. But in this way, you can at least kind of connect and organize stuff. And then on the right, what I'm showing is VSP arrow camber geom shape that I'm going to run VSP arrow on, and then overlaid that on the internal structure. So tip and root capping is important to remember, and it's easy to forget because it happens in the VSP geom, like wing geom, and not in the VSP structures tool. So when you create, if you set the root cap type to be flat, you've now created a rib, and sort of unintentionally created a rib. You can turn this off and it will not create a rib. And that's, but it's kind of sort of default is on. And so it's something to keep in mind. And also, it doesn't show up as a rib in VSP structures. It shows up as part of the skin. So you hide the skin, the rib goes away, and you can't tell that there's a rib there. So it's just something to remember that unless you turn that off, you will have a rib there and a closeout rib at the tip. There is some implications there if you add beams along spars, where it will add beams on the vertical portion of the shear web at that center line. If you turn it off, then it won't do that. So that's kind of helpful. It's not a big deal. And then if you were to turn off the tip closeout rib because you want to put in like an actual closeout rib, just keep in mind that you can't really put a closeout rib entity, a part at the extremity of the surface. So you can't put it at like 801. It'll just cause the thing to blow up. So you have to move it in, one element, whatever your sort of default element width, if it's 1 inch or 5 centimeters or 10 centimeters or whatever you're trying to do, element size, just make sure you keep that rib in about that much so you have room for a strip of elements that isn't microscopic. Currently, some of the tip treatments don't work. They collapse elements in the structures tool. So any of the rounded tips with the extended leading or trailing edge right now create collapsed elements. So, for the moment, you can just use the rounded tip by itself, and that'll at least get you like there's some structure out there and some mass and something to apply loads to. But it won't. It won't be exactly what you're looking for, but that you'll have to kind of do a sort of a different treatment. So spars. So spars no longer overlap across the center line, which is awesome. They used to kind of go past each other, a little bit into either side. And so if you're doing just a left side wing or right side wing by itself, it's not an issue. But when you're trying to run a whole wing structure so you can get torsion, or you're trying to run like a whole aircraft structure for flutter, things like that, or modal analysis, you kind of need the whole wing. And that was causing a lot of overlapping geometry and spurious elements and things that weren't working. Polyspar has sort of solved that. Like Rob said, just recommend using Polyspar from here on out, and it solves all sorts of problems. Even when you don't, even before, when we solved that spar problem, there were still meshing issues around the center line with spars, and you'd have to kind of fiddle with mesh density, and it was sort of unclear what was helping or hurting. But Polyspar, it just works. So Polyspar, awesome. So one trick here a little bit, and sort of trick and also something you might not want, is beam elements remain even after you remove the underlying surface mesh with rectangles. So if you create a finite line and you're going to mesh it, you tell it to add a beam elements to that, then you delete an area with a rectangle by removing the shell surface, you end up with these kind of nice like AB pillars or internal structure. So you can play with that and sort of use it as a way to account for holes that actually have structural, truss frame structural elements running through them. Not so much to the point where you can actually like build a carbon cub welded steel tube fuselage, because you can't kind of go internally and diagonalize things, but it is a trick that I have used. It also can cause you problems, as you see on the right, where I've created a whole bunch of stringers or frames actually throughout the whole structure of this helicopter, and then I put a cargo door on the back, used the delete shell elements to delete the cargo door, and it did delete the cargo door, but it didn't delete the frames. So from a weight perspective, you'll have some extra weight back there from frame chunks that don't exist. And if you're pulling this into like a FEMAP or some sort of a preprocessor that you can, like a fully functional, fully featured preprocessor, you can just go delete those and then run your analysis if you want. Okay, off-body points. So this is a frequent thing that you do in structural analysis for items of mass like engines or fuel or payloads, things like that. You represent that by a single point, and you put either a mass there, or you just put forces representing the G loading of that under like if you're doing a 4G pull-up, then you put 4Gs of your engine weight as a force downwards during that analysis. So that, in the past, you kind of had to do some trickery to get that to work, and now it's really great. You can basically add a fixed point, and you can add it based on the location of any other geom you have in your model. So if you have a block representing an engine, but you're meshing a fuselage, you can pull in a fixed point and say, I want this fixed point to be at the center of the engine geom, and it will put a point there in your fuselage mesh that is representative of the center of your engine geom. And then later in assemblies, you can go back and connect that up to your fuselage, and you have a sort of a representation of a point mass affecting your structure. So this is a really great feature. One thing that I've had to remind myself, it's easy to forget that you can make several structures all from one geom. Sometimes I'll have a fuselage, and I'll make a fuselage, and then wing, and I'll make a wing, and I'll forget, and I'll get into some complicated thing with the fuselage and forget that I need to go, and I should maybe break that out and make like an aft fuselage and a forward fuselage, or a cabin and a tail, or something like that. And the nice thing about this is it's all derived from that same geom. So if you go back into your fuselage, change the length of the fuselage and increase it by 10 feet or something, then all of the downstream structures will rederive from that new shape, and you won't have to be working with multiple geoms and VSP and making sure you're doing the same thing to all of them. So one thing, you will have to later connect separate structures together. So then you have to add a bunch of fixed points to represent that. or you have to go into post-processing and sort of, you know, connect everything together. So it does add scope, but it'll allow you to address different parts of the vehicle differently. So this is a trick. You know, always make an assembly, even if it's just a wing or just a tail or just a fuselage. The reason for this with the MyStran or Nastran workflow, the assembly exports will generate what's called a case control deck and a executive control deck. And you need these not only to open this in PyNastran GUI, but you need them to run the analysis. This is where you define your load cases. So if you run an assembly, there's sort of a default in there. It's maybe a little extensive for what everybody needs without putting a lot of results, but it's a default place and you can delete things from there rather than having to go try and get the syntax right and add that in on your own. So for connections, we're going through connections. Dependent points cannot be associated with more than one independent point. So if you have an independent point, like representing the engine here, and you connect it to 4 engine mounts on the forward firewall bulkhead, and then you later connect one of those bulkhead connections to a person or something, and that person is the independent mass driving to that firewall engine mount. Most of the time, or all the time, Nastran or MyStran will fatal error out on that, or it should fatal error out on that. So that's just something, if you're daisy chaining stuff, you can, you know, daisy chain independent to dependent, and then that dependent is an independent of another dependent. If you really want to get crazy, you can kind of connect things like that, but you can't have a dependent be two things. They're dependent to 2 different independent nodes. All right, so when you are working on connections specifically, you're dealing with more than one mesh, but you're not able to do that. You're not able to, you can create the connections in the assembly GUI, but you're not editing fixed points and things like that in the assembly GUI. So when you're creating the points to use to connect 2 different meshes together, I find that the little drop down at the bottom of the structures GUI here is really helpful, because you can really quickly flip back and forth between your main wing and your flap, or your main wing and your aileron, or your forward fuselage and your back fuselage. And you can do that to kind of line your points up and then later go connect them in the assembly. So when you're meshing, it's you know, it's tempting to mesh it and it looks good on the outside, and you know, just go try and run it. But you really do need to hide things and review your mesh, and we'll go through that later as some sort of methods to do that. But one way to do it is in the GUI, you can go to the mesh tab or the FEM tab, and you can unclick things and you can hide individual components. This is really helpful. You can basically hide the main wing skin. You can hide, you know, panels or rectangles or any components there, and that'll allow you to view the internal structure, and you can see if it's meshing correctly as you want it to. And you can pan and zoom around and look for little tiny elements or you know, bad mesh, things like that. In the case of the root and tip cap stuff, like I talked about earlier, if you hide that skin, that root or tip cap will disappear with it. So you do need to use clipping in some cases to view those meshes, or go look at it in post-processing tools that can sort of transparentize things, and you can look at issues that way. Tapered spars. So with the poly spar, one real great benefit of that when we're talking about the mass fraction stuff is you can actually do a much better representation of a real spar. Real spars aren't a constant width and thickness for the most part all the way out on a cantilever wing, or even like a strap braced wing, the outboard portion as well. So that is really helpful. It allows you to define different property cards for the different sections of the spar, and so you can go through and make a big cap, a medium cap, and a little cap, and a big web and a medium web and a little web, and you can kind of make a tapered spar. And then that'll help you because you're not sizing the spar to the root problem and then calculating that weight or that mass for that spar all the way out continuously to the tip. As with all FEM analysis, there's still typical FEM troubleshooting. So you'll get a nice mesh that you like, and you'll go run it, and it'll explode in the case of like Calculix or ANSYS, or it will solve and give you a really weird look in the case of MyStrand or Nastran, or it will fatal error. So you will still need to iterate with your FEM just like you would with a traditional pre-post tool. With open source tools, sometimes there's issues with the tools themselves, either with the solvers or with the way that OpenVSP outputs its data to those solvers. So, if you start running into things and they don't seem like they're due to the structural FEM that you have built, it's always good to join that community and start asking them and talking with them. They're very helpful, and they can kind of sort out, is it something that is a problem with the tool, and in which case they need to change, fix some stuff, or is it just you're not doing, meshing things right. With the aerostructural coupled analysis right now, when you're using pressures and you're putting pressures on flight surfaces, keep in mind that it will only apply pressures to what you have laid out as your skin part. So with that Quickie aircraft, where it had those panels of buildup or ply-ups on the upper and lower surfaces of the wing, it will not apply pressures to that. So you look on the right and you can kind of see there's no pressures applied to those areas. This is something I think once the new VSP Aero thick, thin stuff comes through, and then we kind of maybe can take a look at the loads part of that and realign that with the loads part, or realign the loads part with that, or update the loads part. This will be a sort of a big component of that, so that you can create sort of sandwich panel construction composite aircraft with different panel surfaces and get the loads onto those parts of the structure. So this is a key one here, and I'll demonstrate this too in the demo. But when you're using aerostructural coupled analysis, the VSP Aero geometry that you run VSP Aero on has to match the scale of your FEA units. So if you build your wing in feet, but in the structures tool, you go say, I'm going to use an FEA unit of inches, your FEM will be built in inches, which will be giant and off in space. And if you run VSP Aero on your wing, which is not anywhere near it, then you'll get a sort of a null result on your loads applied to the FEM because the wing wasn't anywhere near the actual FEM. So this is I think this might be something that we address as well. But you have to at the moment duplicate, and I'll show this on this wing structure, duplicate, create a VSP Aero, a larger VSP Aero in inches that you can, a larger duplicate of your wing geom in inches that you can run VSP Aero on, so that it will have a inch scale set of loads to apply to your inch scale FEM. Okay, so post-processing required. So with Mastran, Nastran, this may or may not be a problem anymore, but for a while there, I had to pass any BDF file that I created out of OpenVSP to through PyNastran, which would kind of clean out scientific notation. To the point where I even just made a little script where it just opened up, read the model in PyNastran, and then exported the model in PyNastran. And that cleaned out scientific notation that MyStrand specifically has problems with. Nastran was able to take that, but MyStrand had dealt with scientific notation for most parameters, most parts of the different cards, but didn't with one of them. I'll also, the current analysis or VSP aerostructural analysis tool only transfers the VSP arrow loads onto the Calculix output file. It doesn't do that to the Nastran output file. Again, that's something that we'll be probably changing to have it send those to both formats. But it will, for the moment, I have a Python script that I'll put up on GitHub for folks that pulls in your Calculix file, pulls in your Nastran file, and then transfers all of the loads that are in the Calculix file onto the Nastran file. And I'll demonstrate that. There's also out-of-plane stiffness defaults, which are 0 for orthotropic and laminate properties right now, which will cause the analysis to run. So I also have a little tool that fixes that by setting the Z direction shear stiffnesses by hand for any sort of nonlinear orthotropic material cards, not nonlinear, but orthotropic material cards, which is the MAT8 card in Nastran or in MyStran. That is not necessarily the right approach for this, and I've listed sort of a better approach, but it requires you to do it by hand from some knowledge of your material properties. So we're not going to do that here, but note that that's a better approach and might be something we put in features to be able to do in VSP structures at some point. In Calculix, so right now it's pretty hard to run these in Calculix because if you create any sort of structure that's got a lot of different components to it, ribs and wings and spars and stuff like that, the naming starts getting really long for the elements, and then that starts causing Calculix to run into name length issues. And in some cases, even if you set your wing assembly to be W and your fuselage to be F and your ribs to be R and everything, it still kind of gets long enough that it doesn't work. So I have sort of migrated more to the MyStran and Nastran approach and left Calculix a little bit to the side in my work, which means we haven't addressed that. And there's also possibly a beam orientation vector issue causing negative Jacobians with a lot of Calculix solutions if you have beams in your Calculix solution. And that might be something that we need to kind of cycle back and get the Calculix stuff working again, fix those things. So just know that right now, Nastran and MyStran is a more, I've been spending more time working with Rob on that. Really, Rob has been doing all the work, but I've been spending more time in that world and requesting things to Rob to fix in that world. So that world is a little more updated than the Calculix world. And then that kind of is an example of that. One last part, so this is the last part of this tips and trips and workarounds here. We're working on improving the connections. When we do a single node to a single node rigid beam, it puts a lot of out-of-plane load on. Typically, often we'll put a lot of out-of-plane load on that shell element, which causes it to fail in some instances. And that's not typically how you would create a connection in a FEM for like a shell, kind of a classic shell and beam representation of a box structure like we do a lot in aerospace. So we'll probably be updating this as well, and I'm working with Rob on what the formulation will be, but it will essentially allow you to, with each fixed point, maybe define a radius parameter, or maybe it's baked in that it'll grab a certain number of nodes, and it will look at those point locations on the structure, if it's on a spar or it's on a shear web or something like that. And it will grab all of the nodes in that general vicinity on that face, and then it will create those dependent nodes to another node that it creates in space in between the two connection points. And then it will do the same thing on the other side, and then we'll connect those two independent nodes together with what's called a C-bush or a bushing or a bearing. And that bushing or bearing, you can define the degrees of freedom, so you can make it a hinge, and basically kind of define how the structure interacts with each other, and also distributes that load onto those faces. sometimes grabbing beam elements, which is hard to do right now with a fixed point. And then that allows you to get a much better connection between the two structures. And so with that, that kind of ends the analysis tips and tricks and workarounds. So if you have any questions, I'll look on here. What's the normal time to process and apply pressures? Okay, I will get into that in a little bit, but the answer is long. With a simple wing here that I'm going to work on, it takes about 3 to 6 minutes, but I've intentionally made the mesh sort of low fidelity, and I've intentionally made the VSP aero mesh sort of low fidelity. With some of the more complex, like a whole aircraft structure and a sort of a what I would say is a more common VSP aero mesh density, I've had it run for like an hour or more, just mapping the pressures onto the surface.